So, okay, let's start.
Wait 1 minute.
Okay.
Wait, this one.
Yeah, so okay.
Please, we'll get arrested if you start telling me Come on. Don't try.
Arrested.
Yeah. Denzel also. Arrested. This time at least you don't have my picture with all the nonsense in front of the dog, which I like.
No, we still have the picture for the last 2 weeks seminar. So we didn't remove this.
When did you take the picture from our website? I don't have it on the website. Oh yes, absolutely.
Actually,
Get a picture. Could you get a picture from him so that we can post it better? Yeah.
I should say that I didn't.
You didn't put the picture. I understand.
I didn't.
Yeah.
I'm not responsible for
You're
the post though.
Of course.
Anyway, so okay, now it's 6:01, so let's start. So
601?
yeah, 6:01. So it's my great pleasure to introduce Gueo from FIU. So he will continue our joint seminar, FIU seminar. We'll talk about generalized Calabi-Yau problem.
Okay, so do they hear? Okay. So briefly, again, as in the last time, I'm going to speak without much of details, and most likely with many kind of, let's say, not 100% correct statement, but more kind of informal. So we start with what was, because I need from the last time a couple of things. On M, sum up from T plus T star, M, away from the, and then such that distinct isometry, and this is the pairing. In the vector space in the dual. And there is this bracket, which I will not introduce again, which is H twisted. Let's say current or Dorfman resonator. And then from J integral for this bracket, which means that classification here splits into plus minus root minus 1, taking from those. And bracket here is preserving them. And since L is isotropic, then it's actually really, so this makes L something which totally out of the way. Meaning it satisfies both axioms totally algebra plus more because it's numbers. Now, the one thing which actually we need is that, of course, one can see this is canonically isomorphic. And then we have the H is mapping. I'll write like this. And then the H splits into from LL bar in this direction. And moreover, the last thing which I will need is J kinds actually a line. This is called pure spinner. And a row defines a grading. And depends on the action. It's like just like algebraic, the algebra is minus k. And although this is a set of forms are not of the same degree. Each one has summation of forms. Now, this was last time. And
so
yeah.
H is a closed free form, right?
Yeah.
And then DH is D plus you take D of the form and you
yes.
Oh, wedge with H, okay.
So again, this mixes the degrees and everything.
Yeah.
But still the H squared is 0 because it's closed and everything. And of course this D is not D for regular forms. It's D for this, which are defined through I mean this works for the forms if you restrict it on the regular forms. This is one the start. Otherwise, this is the definition of the image. Now, from here, this row is actually locally defined, and not up to the constant. And the first definition from the next definition from the last time is well, there is one thing here that the integrable. This is for almost complex, no integrability. Then it follows that the H of rho is there is something alpha times rho. This kind of, yeah. Now, the next thing which is related already with Calabi-Yau is let's say I will say initially. I think this is Nigel teaches terminology. This is called generalized Calabi-Yau. If rho exists globally, and it is 0. But I'll change this to something which more recently is used. Maybe I should say that the results which I'll explain at the end are due to this set of people. Bestie, Jeffrey Streets, there is this guy Ustinowski. So no. and some others which are students of postgraduate. The ones here. And according to them, which is better current terminology, instead of generalized Calabi-Yau, I'll explain why this is generalized Calabi-Yau. But what I will say, which is more precise, is MJ has holomorphically trivial canonical bundle. The reason? Well, let me explain briefly. The reason is if J, basically rho, locally looks like this, well, this exponent B is like a B transform, so and then this exponent is the summation until this becomes the form. So, I mean, the degree is too high. So here omega is symplectic, or it's not symplectic because it's half of them, and theta 1 to theta k are just complex one forms. So if this actually is regular complex, which comes from meaning coming from regular complex, this corresponds to rho. This is global. And this thing corresponds to here theta I as giving you 1, 0 forms. Well, or 0, 1 depends. And this is NDH rho because it corresponds precisely to. So this is exactly what in non-Keller geometry terminology is holomorphically trivial. For most people in algebraic geometry, like our host here, holomorphically trivial canonical bundle is kind of tautology because trivial means holomorphically trivial for them. For us, the trouble is you may have topologically trivial bundle canonical, which is not holomorphically trivial. And this doesn't happen in non-algebraic sense. I mean, for algebraic sense, as long as you have actually Keller space, trivial logically is the same as holomorphically trivial. Meaning there is holomorphic trivialization. But in non-Keller case, actually most of the examples, non-Keller examples, do not have that for trivial bundle, starting with the Hopf surface. So I'm using this as holomorphically trivial. And first, again, is it came from trivial canonical bundle. Actually, if I have to be a little more precise, nowadays this data sometimes is called non-Keller Calabi-Yau, if you want to emphasize that it's non-Keller Calabi-Yau, but somehow to call this generalized non-Keller Calabi-Yau becomes a little, I don't know. And I'm pretty sure Vesti created this notation, so I haven't talked to him, but almost certainly I prefer to keep it. So,
but then what are the example for manifold having this structure?
The regular complex structure with this property is Kudaira surface, the one which I'm sure you know. The generalized complex with this structure, we have many, mostly new manifolds. And if there are not new manifolds, I cannot immediately guess. There are many nice examples of four manifolds which are generalized complex and neither symplectic nor complex, and actually do not admit neither complex nor symplectic structure. Some proper connected sums. But trivial homomorphic bundle is probably already illustrated. Another, let's say, for the regular complex structures, Rayleigh surface is the easiest one, and there is another which comes out of, let's say, principal toric bundles, which is like elliptic vibrations, without singular fibers and without section, over Calabi-Yau space. The easiest one is when you have K3 as a base, and then somehow this is related in a way I'm not sure yet with the Strominger system, which basic solutions are on such bases. Okay. But the idea is new manifolds are pretty much complex, and generalized complex are pretty much related. Not in general, they have trivial bundles. Okay.
And then this is decomposition U minus N to UN.
Yeah.
This satisfy and this gives hot structure.
Yeah, kind of.
So usual hot structure, right?
I'll talk about the usual host structure. Usual host structure for generalized scalar is normal because you have host structure for complex, but you don't have host decomposition. Here, it's kind of weak version because hosts usually have bigrading. Just one. Here, I'm not, let me say, this is K minus N, because this is shift. And somehow, this bundle, which is defined by these local sections, is, I think, this. Let me erase things.
What is alpha? DH rho is alpha a function, or is it, no? It's
No. This is element of T plus T star. No, this is, and this dot means the spinor thing. Clifford multiplication, which is, because this is T plus T star, it's just wedge plus interior, the standard here. But somehow, without the spinor, one cannot talk about that. Last time, I finished with how one can use this grading to talk about possible period domain in this terminology. Of course, this is in a weak sense because it's just grading. But at least you have now. If you want to talk about Generalized Calabi-Yau, which is not just holomorphically trivial bundle, we need the generalized scalar. So the generalized scalar structure in this classical sense means two generalized complex which commute and this map, this I think this is positive definition. Okay, J1. Because the square here, if they commit, the square is plus identity, and because they are compatible with this, actually the plus and minus eigen spaces are equal, and the trace is 0. And linear algebra still. And then, if you drop this condition, this is like generalized indefinite Keller or pseudo Keller, as long as this is non-degenerate. And yeah, I don't think anybody except us some time ago with Oleg, Johan, and Yotov Miro looked at this generalized pseudo Keller. The paper actually got published pretty well in computational physics, but I'm not sure. I mean, it has any really. I mean, there are examples, but no good consequences. Now, the whole point is once you have this condition, this you can split, and you can get that by grading already. H1, again Kj, incarnative and plan, just like the regular function already, but with some restrictions. It's not there. And then dh actually is decomposed as d plus minus where the degree every time here is like 1, 1. For some reason, 1 goes for d bar, but it doesn't have to be. These are not certainly the relation between these bundles and the real Hodge, the real PQ form bundles is certainly there are sums of forms and not only, not necessarily sum of form p-type PQ type forms. I'm not sure. Even for regular terms. So this is like 1, -1. This is the degree where it goes from U at JK, where this goes. And in particular, we have maybe, I don't remember maybe for this one, but this one is certain. If you have generalized Calabi, which gives already closer composition. And as far as I checked, I mentioned it too. I never saw any kind of refinement of this period domain or less. My impression, there is no specific trouble here. There are technicalities which I didn't explain last time, it's like coming out of, in order to have a picture for period domains, you need this type of family of manifolds and deformations. And for that, you need, because you don't have nice generalized complex of spaces and so on, you need this technical language of current algebroids, reduction of current algebroids, things like this. I don't know how well it works, but after a commutation, usually one can adapt. Point is, I haven't seen any application even for the weak period domain, and this is after examples of generalized complexes is a lot. Generalized scalar are very few, and I'm not sure anybody cares that much. So the deformations here are more, instead of deformations, one has this type of, I guess I should explain, maybe I should go first. First I have to go to the Python language and then how the deformations are basically considered for these structures. What happens?
Excuse me, can I
Yes.
ask you, so for example, Hopf surface case or
Yeah.
Kodaira surface case?
They're not generalists. They don't have Kodaira surface case.
Yeah.
How this looks, I don't know. It's not possible. But now, sorry.
No, Kodaira doesn't have
Kodaira surface doesn't have generalized Calabi.
Yeah.
Hopf surface does. But how this looks,
Yeah.
I'm not sure.
How about near manifolds?
No, the new manifold cannot have a general.
New manifolds don't have generalized Calabi.
Invariant, please.
I see.
Only torus.
I'll explain a little bit.
But you can
Basically,
have
about here,
like Sol manifold, you can have.
But anyway, is there any example that this kind of thing can explicitly communicate?
I think for Sol manifold, maybe one can.
I don't know, honestly. maybe for Hopf surface one can do, but and this is, I'm not sure really.
For company group, if you take a
Is
company
there,
group,
but this is supposed to be related with this different cohomology, like every function, all
I
these.
think that company-
And I'm not sure, but I agree, I've not counted for even for Hopf surface, I don't know other calculations for even I agree those. Yeah, I'll explain it.
No, but for some compa simple, I think every is known.
Yeah,
It's
it might
the
be,
guy-
might be, yeah.
The guy recently that Giuseppe Barbaro
Uh-huh.
did that
Okay.
so in that case,
Yeah.
So the H Laplacian is DH star.
Yeah, this is coming with this, which is related to H2.
Yeah, so is there like a generalized Hodge theorem?
Yeah.
So the kernel of
Yeah.
DH must be.
Yes. Yes. The cohomology, I mean, that's the idea.
I see.
You know, still have cohomology. I mean, the trouble is the theory goes perfectly well, but reasonably well. But the set of examples is so tiny that it's not worth to look more into this. That's the reason I believe so far nobody bothers. It's not impossible, probably. Okay, not impossible to even go further with period domains and all of these, but I don't know if that's. So, for generalized scalar, well, the idea is, let me give the next definition. What is a generalized CY structure? This is generalized scalar. Where both they have these holomorphically trivial bundles. Canonical bundles. And to make the things work in terms of examples, basic conjecture which these guys here have is if you have this type of structure, then there is a deformation specific to channel line, which brings this to, and this is in terms of biformation, which brings this to regular Calabi-Yaus, for which the two complex structures are both very Ricci-flat. In particular, if you have two different, you can say exactly how this looks, like hyperkeller, if they are coinciding or with negative and so on. But there is a conjecture that this really is only classical. Now, let me go to these relations.
I'm sorry, but you mean that the conjecture is deformation of this?
In certain general sense,
Yeah.
deformation eventually will produce actually a flow, to be precise, because let's say the first conjecture is that there is this kind of regular Calabi-Yau structure, actually two with the same metric. But the refined one, and this is like from November last year, officially published, announced, let's say, probably they didn't follow. It's actually, you can use something which is called generalized flow, which arguably is supposed to have limit, I mean to have infinite time existence, and then the limit, the result is this type of regular Calabi-Yau structures with the same metric.
So,
Yeah.
what do you mean by having two regular Calabi-Yaus with the same metric?
Don't touch.
Okay,
I'll explain in a second.
okay. So that's fine, I just thought you were.
I mean, he wanted to know about biformation in general. I said yes. No.
but that's in terms of the business connection, in particular,
Yeah.
the reach of the business
Yes.
connection is zero. This
Yes.
business reach flat.
Yes. So this is pretty much with this general Calabi-Yau flow is something which extends the standard to the closed one. And once if that exists for all times, and it's expected that the limit, the structure is let go. And this correspondence looks like this. Or data, which is now write I, J, and B, where I and J are complex and Hermitian. Regular structures. B is a two-form, which I'll explain how it shows. And if we use omega I to be in omega J, I already use this notation, which are the fundamental forms. And then we have this kind of the I operator, which is like I inverse acting after D after I, where this action of I is actually like a group action. Because strange thing is, if you have Hermitian, if you have a structure complex which is actually conductor geometric, then this structure linearly, in a linear algebra sense, it belongs both to the algebra of a special orthogonal group and to the group. So when one says complex structure acts on forms, you have two actions. There's the algebra, which is an N, or there's the group, which is group and algebra actions. So in these terms, this is the first, and the second, I mean, only this data, because B is not involved, only this data are not that hard to find. The difficulty comes from that, which tells you that this Di is minus D. It's actually H plus Di. And from now on, I'll denote this by T, because this will be torsion. Okay. And I can actually write pretty much even how this looks. So I took notes for that. So basically the construction is like this. You have like one half. Then you have this action. Don't forget, these are maps from T plus T star into T plus T star. So that in matrix form they are 2 by 2, but they are block matrices. Here it was standardly I plus minus J, then minus plus J. Here inverse means the corresponding inverse map, because that maps from forms and metrics are maps from one to another. Then this is just omega I plus omega J, as far as I see, and then this is minus the conjugate. And all conjugated would be, if one needs a formula. And then, in particular, this condition leads to and this is already kind of serious restriction, of course, for spaces which are non-Keller. I mean, there are examples, more than the generalized Keller examples, but not that many in these terms. And certainly, I don't think I know examples of these structures which have, I don't remember, trivial canonical bundle regularly. I start forgetting.
Non-business flat.
Just the trivial canonical bundle. I mean, that doesn't have to be business flat, but business is flat. So I'm not sure I can immediately produce. Maybe some new methods can do this. But this is already this kind of consequence of this. It's already not. Now, in generalized Calabi-Yau, there is like a property from two that this, the commutator, well, they put 1/2. Now, G inverse means this becomes a 2 vector, not a 4. The map is not from T to T star, but the other way around. So if one takes this, T star to 2, this will be Poisson. Two vector or structure, such that this thing like sigma plus this is I holomorphic, this is J. So this is kind of the main property one uses one studies that to study that. Now from here I can explain what I mean by this conjecture and then give a little more details. Conjecture means if you have deformation, now the formation of generalized Calabi-Yau structure means somehow the formation of this. And in fact, there is specific type of deformations where one complex structure is fixed, and this vector, Poisson vector, is fixed. So you deform the second, the metric, and the form. And if you deform it in a specific way, which actually is corresponding to the generalized Calabi-Ricci flow, the idea is that at infinity, what you get is same thing, but this is the Ricci flat and this is Calabi. That's the okay.
So the
One
metric is
metric.
the same.
No, metric is new. So the idea is
So with the metric for the two Taylor structures.
For the two Taylor
if it is
structure is the
yes.
same.
So the conjecture I can say in let's say first in the first form is one can form in a specific way or such that G, let me say deformed I form J deformed have this property that actually I deformed is the same as I, and G deformed J deformed, just like J deformed and Ji are plus Ricci flat bound.
So,
It's the same metric.
so you take,
That's
if
it.
you take the metric and the complex structure, you get a Taylor form.
Yes.
So these two Taylor forms are not comonomous. Are Are there any known examples of
Actually, for this, one can say all known examples how to reconstruct. There is, this is something which is usually called Bournemont-Bouville theorem. Now, this thing here and can be up to, this is finite cover. Maybe I should write down here. So, M, which is actually hyperkeller, times M1, for which I deformed is minus J deformed, times M2, which is a plus, times toroid. So this is type of Bournemont-Bouville theorem. The easiest way to imagine is the first Dirichlet plot that reduces the structure group to SU. The second is to reduce to a subgroup. And this is okay. Where in this case, because one has sigma, holomorphic plus 1, it's relatively easy to understand that these two come out of the kernel of that. And this is where this is known the general. So that this is giving holomorphic symplectic, and because these are keller rich flat, this is necessary hyperkeller. And here, this is 0, but they are still keller rich flat.
But you assume that you start with generalized scalar, which is holomorphic.
No, this is,
You just assume, okay, okay, that's
let's say maybe it's a gen
just
CY structure.
Okay, you just start with general. Okay.
Start with this.
Okay.
Existence and so on. Now let me explain roughly what's the strategy here and basic examples.
so we start with
So that we can go.
the old J1 and J2 are generalized complex structures.
Yes.
And then in the limit, in this flow, they're going to be honest complex structures.
No, not exactly. Both are genuine, generalized, they are genuine, but they define the regular ones.
Oh, I see.
And these ones in the limit
I see.
will be
So
the.
that's okay.
So, but also, so in the end, in the limit,
So, yeah, actually,
zero.
you're right, sorry.
Yeah.
I'm writing this kind of non-property.
Okay, now
You define, of course, these are one and one and the same thing.
Otherwise,
But this deformation gives you this deformation.
I see.
And this deformation, this is what you get. So when you go back from this to that, I guess they're already again.
So I guess what I was going to ask is, so the limit, if you're getting honest Calabi-Yau, then the C1 is 0, but the I and the J are changing, right? Or maybe one of them doesn't.
One doesn't, but the other does.
So are they? Is it always true that the fire mission for I and J, the C1 is 0 for both of them?
I think. Yes. I'll explain. Yes. There is. I'll explain directly with the formula. But I'll have to get to details. 50 means some of that. So how this works?
so the conjecture is open. They didn't.
No, but what they did was basic estimates. Of course, there is this unique thing, and I can explain how this structure is supposed to look. So there is one more definition here, because this is generalized Calabi-Yau structure, and generalized Calabi-Yau structure simply means, well, we have something with, the usual Calabi-Yau structure. The usual thing is we have Keller space. So we have one complex structure, one Keller. The basic example, of course, this is general Keller because one is complex structure extended, the other is the Keller form, the symplectic form. So in these terms, a way to look at the Calabi problem.
just to understand better, they form using the sigma, the Poisson to vector or not? Because otherwise you need the two do not commute, right?
That's the whole point. No.
So
They
they
don't,
don't need.
but eventually the Poisson is preserved under the formation.
I see.
Initially, it was.
Oh, okay.
Yeah, after I explain, maybe it will be a little more clear. So the idea is if we have I complex plus omega, which means omega is n0 for closed, omega I tethered. Then the Calabi problem, or maybe Calabi-Yau, because Yau solved it. So whatever
You still call it.
you can say, he's student of Yau, so I'll let him decide on the terminology of this comment. Is the same as find when this one equals to constant, where this is with root minus 1, or 5, right? Okay. Now, so in this form, and I mean this of course works, how one defines the same for generalized Calabi? So the next terminology which they use is maybe, let's say, generalized. We say that M has generalized Calabi-Yau geometry. What does it mean? Well, this, in fact, one can rewrite in the following way. We want the generalized Calabi-Yau structure. And suppose that these are the corresponding pure spinors. Then we look, well, formally here one takes log, if you remember, to have better idea, so I guess I should put log here, and sometimes even for some reason they want minus for better calculation, but so take this. These are all global. These are this being constant is not Calabi-Yau structure, but geometry. And the regular Calabi-Yau metric is that thing.
So this is the pairing, not the general.
And this one, maybe I should explain it better. Sorry. Is something which is called Mukai. And this in terms of, because these are spinors. Basically, this means there is some involution here, the top. So this is not a number, these are the forms. And this S is pretty much, when we have a product of spinors, this is reverse symmetry. I can write it in terms of form because this is, in this case actually is not that hard. Okay. And this is like reason how. Of course, this fits, but one is exactly, if J1 is exactly complex form, complex structure, then this is the corresponding pure spinor. If you remember, the pure spinor look at the symplectic part and these forms theta 1 to theta k. The forms correspond to the complex part of the generalized complex. The other one corresponds to symplectic. So let's say if you have only symplectic form, because it's closed, and then for symplectic form, of course it's global. And this is kind of Calabi-Yau, general Calabi-Yau structure. No, not general Calabi-Yau structure, it has trivial homomorphic component, generalized. So it becomes even more kind of unnecessary to say that this is general Calabi-Yau. Should not. I hope I'm not right, but this is what I remember. I have to check if I'm correct. So if you need me, if you need this fact, you have to check. So
actually, this guide pairing is generalization of usual guide pairing.
I guess. Yeah, I suppose. Yeah. Usual Mukai pairing is exactly, I mean, because this is for the forms anyway. This Mukai pairing is exactly for the forms what we know about Mukai pairing. The same thing. Don't be happy. Don't worry. There are no examples. Don't trust.
Okay.
Don't be too optimistic, let's say. It's early.
You are very pessimistic.
Yeah, she knows. Now, I'll go a little bit. One way to solve actually the problem, which came much later, is in fact to use the flow. So to use a flow here was like you take omega t. This is for regular Calabi-Yau, just usually.
Non-generalized.
Yeah. And then this one being a constant, one can say that you can use and then this is determinant. I think it was G. This type of flow. And this is kind of Keller-Ricci flow. And this is this type of Keller-Ricci flow where the Keller class is fixed. In general, for Keller-Ricci flow, one can flow the class and the potential, while the purely subharmonic type. But to flow the class, this is finite dimensional space, you can do it kind of separately. As far as I remember from the very early things. So this is enough as the deformation to get to the result. So Keller-Ricci flow for infinite time, existence and the infinity you have here. Yeah.
So the deformation is through this flow.
Yes. Here, of course, this is before you take dD bar of this is Ricci. dD bar of this is, so this is the Keller-Ricci flow. Well, one needs minus, I think. And sometimes they put 2.
Yeah.
Okay. And the whole point is how this translates in general terms. Well, here one needs to understand a little bit more what's the meaning of Keller class. Of Keller class, this means like open cone in a linear space. But for generalized, it's not linear at all. Well, some of it is not linear. And well, I'll give the basic definition here for that class, but
homology, right?
huh?
You use the F homology
let me give you for that what one can do is use actually a paper published in the journal Complex Manifolds. Just recent history.
Oh, yes, yes.
You remember now?
Yes.
She's the editor-in-chief, that's why I'm reminding her that she should know the paper better than me. You know?
Yeah,
She's the one responsible for the paper, I'm not. I wasn't referee, I promise. I can announce easily. So, there is something which is called analog of that class. You can consider this as like a deformation with this T. So there is something in the generalized scalar case. We start with generalized scalar. And well, for this particular name, I suppose there will be change anyway, because there is something which is called canonical deformation. Did you refer the paper?
No.
Okay. But you know it.
Yes, yes.
So, what is canonical deformation? This is pair of these general complex structures. To satisfy this, and I'll write down here K, T, and the same is for J2, where K, T is 2, 4. Now, one can translate this into deformation by definition. And I have somewhere here the by definition transformation. I guess let me write it like this. And then IT. So there is a basic result in this paper. So that this is by Hermitian. Also one deformation which preserves the by Hermitian structural vectors. If like is in lambda 1, 1 of JT closed. And is there anything else? No. This condition. And from this condition, it follows that IT is the same as I. Remember? Then I have formulas for JP general. No, I don't need formulas much because I will use actually particular form. Sigma T is the same as C. This one, these things I will use anyway. And then the crucial point will be instead of general form, to use this Ricci form here, which will give exactly the generalized Calabi-Yau form, which is ended up with more objects to deform than just the method. Okay? But before that, the basic examples of this type of canonical. I'm not sure this canonical will stay. Not exactly canonical, it's not really. But the basic examples are, of course, if you have omega just scalar, then omega IP is omega plus exactly this type of P. Okay. IT is the same sign. So IT is everywhere at the same time. This is the first. The second is precisely if these two structures commute. This is where Vesti, Postulate, and Markov end. Then actually if this commute, one can say that the tangent bundle splits as a sum of holomorphic sum bundles, where they are equal or not, for the first one. And for the second, we don't have. And then for this, again, we have pi t sign. I believe j t is also, I'm not sure. Yes, jt is the same. And omega I t looks like omega I. That is t. I have this minus of a function.
So you only change the metric.
Huh?
You only can change the metric here.
No, you do change the name.
Yeah.
True.
Yeah.
But this is very similar. And the third, I mean, these are kind of external cases. This and the other is when, the third is when sigma is non-degenerate. In certain sense, this is kind of the generic case actually, but then you have holomorphic symplectic form. And then if we have this family of functions, then it has this for that holomorphic symplectic, omega Hamiltonian transformations. And this is actually the first type of deformation which we had in our paper, but actually Joyce pointed out exactly this setup. Initially with Vesti and Miluchon, when we wrote the back-dimension paper, first we didn't know about the physics. And then second was, in order to construct, we use some kind of deformation, which works in K3, but we didn't have that picture. That's why this picture is called like Joyce deformation now. Joyce, what? Well, I will tell more, but yes. I'm recorded, so yeah, I don't know who is going to arrest me next. I will tell not now. So here again, jt omega t is omega. So sigma inverse t, sigma t inverse is not changed, just like you see here again. And then j simply within the fourth, same is omega. And then g. And same with g. Maybe I should write down g. Sorry. This is pretty much the first time we realized that the bicognition structure actually exists. At some point we weren't sure whether bicognition is equivalent to self-drive. All this kind of no. I mean, we knew about Hopf surface, but for any other. For Hopf surface, it was not.
The deformation that you consider was on the complex surface, or was on the complex surface?
We looked at bicognition for complex surfaces because complex surfaces, the question is, in fact, you look at these by Hermitian conditions without the differential condition.
Yeah.
And only out of them, what you get is that you either have the second, or you have, instead of the second, the differentials are with plus. So, and with plus are hypercomplex. With minus is this, like left and right invariant structures on the key groups and things like this. So in these terms, and basically these were kind of considered before, not just that. This is, I don't know whether this was taken on basic or whatever, but yeah, this is kind of natural information. And oh, I'm already late. We're missing dinner. So what I'll explain briefly is for example, the conjecture is that when, let me write down conjecture too, if K is actually a Ricci tensor of the bismuth connection. Here, bismuth connection is like the Levici vita. B comes from bismuth. Name which he doesn't like. But anyway, as far as I remember. Yeah. But the reason we called it bismuth first is we first saw it in. This is the Levici vita. Plus, actually, the torsion after G. Where T was, if you remember, that H plus dB with 1/2. After G means you need to see the tensor. I mean, this is T form, so you need to uncouple and raise the implicits again. And then you have curvature, and then you have, it's like the curvature of, this is like a trace. And then you need I here. This is G. G, summation over I, like this. And this is, of course, rho B. Yeah. Because I wanted to finish faster, of course, I'm finishing much slower. It's called bismuth. And well, bismuth Ricci Stroninger depends on the corresponding alphabetical order, but anyway. Even if I record it, I have to make this disclaimer. And the conjecture is, which is a refinement of the conjecture one, that the flow, so the canonical deformation for rho of D BK, which gives, in fact, this canonical deformation is a flow. The canonical deformation rho BI has infinite time existence as a flow. And exactly this G infinity, I, because I doesn't change, is not changing, then J infinity, D infinity, have this Keller-Ricci flow.
But rho B is in general not of type 1, right?
No.
But then if you flow that, you impose that
True.
condition.
So this is kind of not precise. The flow actually here is slightly, not exactly. It's
Okay,
related,
because
but no.
that's- Yeah.
It's not, of course, no. Well, let's say there is one useful formula here. If we have all of these Calabi-Yaus and so on, then of this function phi, if you remember, phi was that minus log of something, which is not necessarily constant. In particular, first class is 0, of course. This is relevant in the first class, it's admission connection. So this one is admission connection, meaning preserving the complex structure, so that this thing here do represent first class. They are closed forms always. And if they have this time, because the first class is 0. So to answer the question from before. This is all in the paper from November. So
Which paper?
I'll give you the paper.
Yeah, you have to read more text.
I'll give you the paper.
I didn't read the paper. Okay.
I browsed it only for the talk. I wasn't reading it otherwise. Okay, and yeah, there are some estimates for that. There are for this case, there is a previous paper which already is published in Trevor, I guess, where you have a little more, but still not complete solution for that. And they have some strategy additional here. Follow the, maybe let me see if I can write as well. Because for the form, yes. So this is not precisely that. This is in fact Generalized Calabi-Yau flow.
Okay, then
And
they
then-
flow also the free form.
This is kind of related to K, of course,
Okay.
distance, but the idea is the Generalized Calabi-Yau comes with this, basically. So I will write it like this on I, and this is 1, 1. And B is, and this is 2, 0 plus 0, 2. And then actually this derivative is in fact this theta by J add this V4. Only this part is blue repose, as far as I know.
Yes, yes.
From Streets and Young. Okay, so at least use this flow and actually prove some conjectures. As I explained, the conjecture means generalized scalar.
But
Or
the
generalized
conjecture
Calabi-Yau is not generalized.
is open, they didn't prove the conjecture.
No.
They
Of
formulate.
course, one can do more. I mean, one can say something about like what is this space of generalized scalar structures in this canonical information, so it will be talk about there is this analog of constant scalar curvature metrics. I mean, in generalized sense, there is no generalized correction and curvature, everything straightforward to get the, I mean, there are, but not possible to talk about reaching scalar. but just like the scalar curvature is appears as a moment map in the carrier class, one can talk about moment map for generalized carrier, although this space is nonlinear. And I mean, space of equivalent to that transformation. This space is nonlinear, but one can still talk about moment map there. And kind of define scalar curvature as moment map. And one can say scalar curvature flow or things like this. This definition for scalar curvature is by Gueo. Okay. Go ahead. Sorry. Stop the recording.